The chain rule is a key concept in calculus used to find the derivative of composite functions. In this video, we will break down the chain rule step by step, and we will also tackle some of the most common mistakes that people make when using it. One big misconception about the chain rule is understanding what a composite function really is. A composite function is created when one function is nested inside another. The chain rule gives us a way to differentiate these types of functions. Consider two simple functions. Say we have f of x equals x squared and g of x equals x plus 1. These are separate functions, but if we can use them to form a composite function, we can substitute g of x into f of x. So, replacing every x in f of x with x plus 1. This is a classic example of a composite function. Identifying composite functions, especially when they're more complex, is essential. So, how can you tell if a function is composite? A useful trick is to ask yourself, can I break this function into two functions where I substitute one into the other to get the same result? Let's try an example. Say we have h of x equals sine x squared. Can we break this into two simpler functions? We can let f of x equals x squared and g of x equals sine x. Then, if we plug g of x into f of x, we get our original function back. Understanding this process of decomposition is crucial before applying the chain rule. The chain rule helps to differentiate a composite function where one function is composed within another. Essentially, it tells us how to take the derivative of the outer function while respecting how the inner function behaves. This can be represented as follows. This means that first, differentiate the outer function f while treating the inner function g as a variable. Then, multiply the result by the derivative of the inner function g of x. But how can we differentiate the function f while treating the inner function as a variable? Assume that we have a function f of x equals x cubed, then the derivative of that function would be 3x squared. Now, what if I change the term x with something like sine of x? Then the derivative will still be 3 sine x squared. Note that in the last case, the function f of x is a composite function. Thus, according to the chain rule, we multiply our derivative of the outer function with the derivative of the inner function, which results into the following. Since we understand the concept of chain rule, let's generalize it. The concept of chain rule can be extended to functions with multiple layers of nesting, where you apply the chain rule recursively. Now that we understand the chain rule, let's dive into multivariable chain rule. In multivariable calculus, the chain rule is extended to partial derivatives when functions depend on multiple variables. The chain rule for functions of multiple variables can be written in different forms depending on the context. For example, if z is a function of x and y, where x and y are both functions of another variable, the chain rule is applied as follows. Here, the term dz over dt is the derivative of z with respect to t. The terms partial z over partial x and partial z over partial y are the partial derivatives of z with respect to x and y. The terms d of x over d of t and d of y over d of t are the derivatives of x and y with respect to t. This formula shows how the total derivative of z with respect to t is influenced by the rate of change of x and y with respect to t, as well as how z itself changes with respect to x and y. Suppose z equals x squared times y, where x equals t squared and y equals 3t plus 1. We want to find the derivative of z with respect to t. The first step is to apply the multivariable chain rule. Then we can compute the partial derivatives of z. After, we differentiate x and y with respect to t. And finally, we substitute all values into the chain rule formula and simplify. Thus, the derivative of z with respect to t is the following. By understanding the chain rule, you can gain a powerful tool for tackling complex derivatives where functions are interconnected. This allows for more advanced analysis in both pure and applied context. And this is it regarding the chain rule. Do not forget to like and subscribe if you benefited from this video. Thanks for watching.